very small recap of last time. So we began by we're looking at these families of Calabi-Yau toric Fano manifolds. And then we talked a little bit about these amoebas and how they approximate these toric varieties. And one major point with this is that for small t, these Calabi-Yau manifolds, they contain large regions which are biholomorphic to annuli. So they're the inverse image of some, under the log map, of some open patches in Rn. More precisely, what they would be, these open patches, or what they are is, so these would be subsets of P sigma of star M sigma. So if you remember from yesterday that there is this way of near a vertex in this polytope, you can define an affine coordinate map on the star like this. And you should think about these annuli as sort of just the inverse image on the log of these subsets of these regions. And it is when you in these toric, in these Calabi-Yau families in toric Fano manifolds, it's natural to look at two different types of annuli. On the one hand, so by fixing a phase sigma in the moment polytope, we get something on the star. On the other hand, we can also fix a phase here, and then we get something. So we usually look at P sigma of the interior of phase tau. So now tau is a phase here. The sigma corresponds to one vertex. We use sort of the same coordinate map we use in a star, but we only care about the open phase.
You said phase of momentum confused me. Shouldn't it be a vertex?
So
that's
vertex,
a dual momentum polytope, right? So
this is a dual, yeah.
So the faces of this guy, which should correspond to this annuli or facets, should correspond to the vertices of the momentum polytope.
Yes, that's correct. And what I'm doing on the left hand side here is fixing a face in the moment polytope, and that gives me a coordinate patch in the vicinity of the vertex corresponding to that face.
Okay.
And then
I see.
In the second one here, I'm fixing a face here, and then there is a choice of several different coordinate maps, each for every vertex. I'll also I'll sort of try to mention these more general settings again by looking at semi-stable simple normal crossing models as well. So if we have similarly to this point here, if we have a degenerate family, so maximally degenerate Calabi-Yau family, with a model which is simple, semi-stable and simple normal crossing. Then XT similarly contain large regions, biholomorphic to annuli.
Can I ask for this large? What's large mean? Is it large as? Because yesterday I understood that some of them actually are small.
It depends on what kind of perspective you have. If you have the perspective of the Calabi-Yau metric, then they are large in terms of volume.
One of them are large and the other are small.
So they will all be large. These.
Okay.
So one of them would be sort of entire faces. The other one, the right one here, would be the image of entire faces. So they are large.
Both are large.
Both will be large, yeah. Because the left hand side here, we're looking at something in the vicinity of a vertex, but it will contain sort of non-trivial open parts of the open faces. So they will contain volume even in the limit. So let me try to finish this thing here. So let me just do this. So similarly, XT contains these large region biolomorphic to annuli, but we get just one region for each phase tau in the dual intersection complex of the central fiber of the model. So that the last part there is just what being simple normal semi-spatial simple normal crossing means. So these deepest intersections, you have these patches which are like large annuli. Secondly, which I didn't talk about yesterday, at least not explicitly, is that so sort of by a junction you can understand, you can write these holomorphic top forms on the Calabi-Yau, and they are approximated by the holomorphic top form on the annuli. And similarly, in this more general setting, by a junction, the holomorphic top form so then not on all of these faces, but the holomorphic top form on annuli corresponding to faces tau in this essential skeleton. The holomorphic top form on those annuli approximate the Calabi-Yau top forms.
But this is only one type of this anyway, right? On other ones they do not.
So in this more general setting, there is no, or at least I'm not talking about. I'm only talking about one type of tora, the one corresponding the open faces.
Of the log.
So essentially, only the open faces like that. Yeah.
When you say approximate, so you're thinking of this essential skeleton to have some kind of topological retraction map on a big part of your Calabi-Yau close to t equals 0?
The closer t equals 0, there is these large parts of the Calabi-Yau
that actually has a fibration over that.
Yes. And of course, when I have an annuli, I can write down a holomorphic top form, and then more or less explicitly you can see that they approximate each other to C infinity. Then solutions of this Monge-Ampère equation, which I talked about earlier, they give calorimetrics on the ambient space Y. And if I restrict them to xt, then on these large annuli, these are semi-flat Calabi-Yau, which means they're Calabi-Yau metrics, and they're also torus invariant. They're given by a solution to a real Monge-Ampère equation. And then the more general version of this is that if you have a continuous semi-positive metric on polarization of this family of maximally degenerate Calabi-Yaus, which satisfy a real Monge-Ampère on open faces of the essential skeleton. Then this gives, so in this toric setting we get an actual metric on the ambient space which we can restrict, in this more general setting, there's no ambient space, but you just start with the maximally general family of Calabi-Yaus. Then what's needed and what Yang uses is he approximates this continuous semi-positive metric by Fabini-Study metric. So gives a Fabini-Study approximation. On xt, which are in this case approximately semi-flat Calabi-Yau on analyze.
So can you approximations of xt approximate? Can you say it again?
So the Fabini-Study approximations on xt. So yes, so this fs.
So can you elaborate on this?
Sorry?
Can you elaborate that phrase?
Yes. So a key point here is that this metric on the line bundle needs to be semi-positive, which is equivalent to being that you can approximate it by Fabini-Study metrics of global sections on that. And those global sections, they're defined on xt. Those you can sort of use them to pull back these non-Archimedean objects, which is really sorry. So I should probably say, so what I'm looking for here is a continuous semi-positive metric on the Berkovich analytification. The Berkovich analytification of these objects. So this is really, I mean, this is a non-Archimedean object, and the way to go to pull this back to something which actually lives on our Calabi-Yau manifolds, to put it back from the non-Archimedean world to the Archimedean world, is to first approximate it with Fabini-Study metrics, which is this algebraic object. So global sections of L over X. And then these algebraic objects, you use them to produce these Fabini-Study metrics on XT.
So somewhere implicit is probably that you need to go over to a high power of L.
Yes, good point. So if you have a continuous semi-positive metric, then you can approximate it if you sort of take high power of L. Yes, this is important.
Does this continuous semi-positive metric on the line bundle on the identification have some uniqueness properties if they exist because the Calabi-Yau metrics?
You mean this continuous these
exist,
metrics on L
yeah.
on the analytification? Yeah. Yes, they are unique. Yes.
So they are unique.
Yes. So there is only so essentially it's unique. So here I'm talking about the real Monge-Ampère equation.
Yeah.
If you talk about
Real,
yes, and then nothing is known about uniqueness, but the uniqueness is known for the non-Archimedean Monge-Ampère equation. So and that's one of the complications here, because so let's see if I have enough. So here I'm really asking for something that honestly solves a real Monge-Ampère equation. And an important part of the context here is that there's a non-Archimedean Monge-Ampère equation which is defined algebraically in terms of intersection numbers, and this is known to have a unique solution. So by Mazzon, Fabre, Jonsson, there exists a semi-positive continuous semi-positive metric on L solving is unique semi-positive metric on L solving this is of course a very good candidate here, because it would be natural if something solving the non-medium multiplier equation solves the real multiplier equation. So there are connections there, and there's also a result by a student of Hubler. Yes, so there's a result by a former student of Hubler, Wilsmeyer. Under certain conditions, under a technical condition, this solves the real Monge-Ampère equation. So there is, I think this makes people very excited. Been a lot of sort of interest in actually proving this technical condition. Because if you can prove this technical condition, then you know that the non-Archimedean solution to the non-Archimedean Monge-Ampère equation solves the real Monge-Ampère equation, and then you can run young Lee's machinery to prove these weak matrices by SYZ-conjecture. But it seems hard to prove directly, and it has been verified in cases, but whenever it's been verified, it's always been in these toric settings, microsettings, and it's always verified by first solving the real Monge-Ampère equation and then sort of using that to produce it. Unfortunately, but I mean, there is certainly hope to prove it with a direct non-Archimedean approach as well, I believe, but so far it's not been verified in any example outside of the work.
Yeah. So I got another question. So from this solution of, so imagine that you take the solution of the non-Archimedean Monge-Ampère equation, and can you read now the real Monge-Ampère equation? The metric is given by a potential. Can you guess the potentials in different zones from the solution of the non-Archimedean Monge-Ampère equation?
Oh, you mean if you can guess its behavior, or what is it?
If you can guess what is the potential, for example, in the phase of the world.
Yes, I can say something about that, but I will not use the non-Archimedean Monge-Ampère equation. So even the solution to the non-Archimedean Monge-Ampère equation is possibly even more non-explicit than the real, or more harder to sort of get that. It's very much the way it's proved, this existence, in particular the existence result, it's based on they kind of mimic the variational approach to complex Monge-Ampère equations, which is, I mean, it produces very non-explicit something.
But then why should it be helpful at all?
This solution to the non-Archimedean Monge-Ampère equation. It is, I mean, it's certainly a very good candidate, but okay, technically, I'll mention one case where it's been helpful technically, but there's still some, it's not quite there yet. Okay, so I want to say also something about how these essentially these 3 bullet points, how they are used in Japanese machinery. So here, this will be, I mean, here I will be, I'll try to, I'll not be able to explain all terminology, but I'll try to sort of explain the gist of things. So, the proof is essentially, or the first step in the proof is to show that these potentials of the Calabi-Yau matrix are approximated by these solutions to the real Monge-Ampère equation. And the first step in that is to get CCR estimates to show that the potentials themselves converge, and then you need higher order estimates that the derivatives also converge. But in terms of CCR estimates, these this theorem sort of summarizes the main points, and it's in this current form it's due to Yang Li. But you could also think of it as like a general statement that comes out of L1 stability estimates for complex Monge-Ampère equations. And this is a pretty large industry that started with Kolotchev's, with some work by Kolotchev's in the late 90s, so 98, I think. So he used this to prove that if a potential has the Monge-Ampère measure of a potential is in LP for some P, then the potential is continuous. And he used this to capacity estimates for these Monge-Ampère measures. So which was a new technology, and it's sort of fundamentally different from the estimates that Yau used, for example, when he found the Monge-Ampère in the smooth case. And what it says is that if we start with the compact Calabi manifold, and we have a continuous omega plurus of harmonic function, an omega plurus of harmonic function, then it's just such that I d bar of u plus omega is semi-positive. So then so if we have a calorimetric omega, and if you take another calorimetric which is in the same Durand class, then you can express it like this for some u which is smooth and strictly plurus of harmonic. So this is these omega plurus of harmonic functions that somehow is used to describe all the other calorimetrics in the same Durand class. But since we're only demanding this to be semi-positive, it's some kind of closure of the Durand class, or the closure of the set of scalar forms in the Durand class. So if we have such a thing, and we also have a Skoda estimate. The Skoda estimate it's an estimate on this type of integrals. The Calar form is right here, and then this given an estimate on. Essentially, we want a Skoda estimate. It's something that there exists a uniform constant, little and lowercase and uppercase a.
For every omega.
Exactly. For every omega plurus of harmonic function. This estimate should hold. This is like a very uniform thing. And there. So a few more conditions here. So we want if we look at the sub-zero set of U, it should have some volume. I'm fixing the volume here. And I also want the total variation of the volume form of omega and the volume form of U to be, the total variation of the difference here should be small.
So what is S?
It's just a parameter that's going to convert to zero.
There is no S on the left hand side.
No, no. So it's just a parameter. But then when we apply this, U will be the difference between the potential of the Calabi-Yau matrix and the potential of the real Monge-Ampère matrix.
And then you found the S.
So then this will depend on T, and then there is a relationship between S and T.
But what is S?
It's just say I think what you have here might be T. So it's like T.
T is another thing that doesn't exist.
No, but logically it's a
It
statement,
will.
right? So
Oh.
you have S in the assumption, you get a statement. So
No,
freedom of
but
U is
okay.
bounded by
So
CS.
these will depend on S.
Yeah, maybe US, maybe U is S dependent. Is that?
So how about I remove this and just put a constant here?
Yeah, I think it's just he's assuming there's an estimate in terms of S, and then the statement depends on S.
Yes. Thank you.
Uh-huh.
We also
Just
want
read and complain.
some technical assumption. U should be smooth away from the zero set, and U should be bounded with zero. T0 norm. Then the supremum of U is less than or equal to constant times S. So S will convert to zero. This will say that it's said that you use these omega pairs of harmonic functions to represent scalar forms. But there is an ambiguity there. If I add a constant to my potential, then I get the same scalar form. So when you work with them, you usually pick a normalization. That's how do I normalize my potential? And this is a way to, that's the way to think about this, in particular about this condition here. So what we're doing first, we're choosing a normalization of, so this is my manifold xt, and here is my u. So I'm fixing a normalization. So, and I make sure that at least part, that the sub-zero set is not too small. So part of it is below 0. So I have something which looks like this. And I make sure that I always keep a certain uniform amount of, so I'm going to let t and s tend to 0, and then when I do that, I make sure to always normalize, so I always have a uniform amount of volume. And what this says then is that the supremum, so this line here is going to convert to 0. So one way to say this is that u can only deviate from its maximum on a very small set. So by large probability, u is close to its maximum. And I think what's remarkable about this is how little information about u actually goes into this theorem. The main part is really this thing here. So it's first of all, it's only concerned with the Monge-Ampère of u. And secondly, it doesn't give any uniform bound or anything. It just gives a bound on the integral, the total variation. So it's like a very, very coarse bound. And you also have you need a C0 bound on A. But if you think about what happens if we let S tend to 0, then we get something much stronger than the C0 bound. We really get that supremum. We get full control of the supremum. So it is, it's somehow remarkable in that sense that there's so little information, such a coarse bound on u that goes into this. But as long as you have these other estimates here, the Skoda estimate, for example, you still get them.
Could you elaborate on the Skoda estimate? When is it? So do I read this correctly? That's an assumption on x, omega.
Yes, exactly.
So what are criteria when this is fulfilled, and when may it not be fulfilled?
So it's always, there is always such a Skoda estimate if you fix a Calabi manifold. But what we will need later on, because we will vary, x will depend on t and omega.
Oh, the point is there the little a and capital A go into your estimate.
Yes, exactly.
I see.
So my c here depends on little a and capital A. So this is a very good point, and it's really the next point here. That this is also a theorem by Yang Li, that if we have a maximally degenerate family of Calabi-Yau manifolds, then there is a uniform Skoda estimate for all of them. And that's also pretty remarkable because so this is the worst way we can degenerate the complex structure. And still we have this control on the pluripotential theory on x of t. This is for me, and I think for many people, this was very surprising. And then, so as a corollary of this and the previous theorem, then we get this fact that if I look at the difference between the Calabi-Yau potentials on xt and this potential I get from my real Monge-Ampère equation, then this is near its maximum with large probability. It can only deviate from its maximum on very small terms.
That was a question from your previous slides.
Yes.
You were highlighting integral estimates. Where are you integrating this on xt?
Yes, I am. But I'm integrating on x. So the way I've written this, there is no xt. There's really just a so there is an x, which is just a general Calabi manifold.
But isn't that cohomological? So the R or the same?
No, if I integrate just omega, so So sorry, this is, I need an absolute value. Okay, thank you. Yes. I'm glad we caught that one. So this tells you that they are close on most of their mass. They're really close to each other.
I was wondering where L1 comes from. Is this the L1 in the?
Oh, the L1 stability. It's just that the L1 means like a C0.
Yeah, but
we're bounding the.
But isn't that the L1 norm that you?
Oh, okay, yeah. Fair enough. So I'm actually so. Okay. Yeah. Maybe I can elaborate on that later on. Why it's called L1. So. And this is also exactly what we get by knowing, with these implicit computations of the top form. This is exactly what we get. We get that the top form on the underlie is similar to the top form on the Calabi-Yau on a large region, which contains most of the volume. So from that, it follows immediately that the total variation will vanish. It's really like what comes out of this zero potential machinery is really this corollary. I mean, this is the main point, that the difference here is near its maximum with large probability. But of course, we're not done there, because I mean, we could have something that looks like what I drew before, something like this, or it could look like. But essentially, we only know something about the size of these sets. I mean, in principle, it could deviate a lot here. So it cannot deviate so much on the actual analyte. And this is because, first of all, we have some control on this thing. This we get this from the solution to the real Monge-Ampère equation. I mentioned that the gradient image of this is going to be the moment polytope. That means we have a Lipschitz bound on that. So we have some bounds on this one, and then it follows from the mean value property of subharmonic functions. You cannot deviate so much here. But to apply that, you need some kind of, you need to produce some kind of disk to apply this mean value property to it. So you need some kind of control on the complex structure, and this you only have on this analyte. You don't have that all over everywhere in analyte. So you get that you have these C0 convergence then on the analyte, not in general, but on the analyte. You know that they're close. The next step then.
So they should not be close like everywhere.
No, probably not. Or yes, I would say, I don't know. I don't know if they're close everywhere or not. It's not known. So next step then is to upgrade these C0 estimates to C infinity estimates. And this is done by a sort of small perturbation theorem by Savin. This is sort of a separate community. This is very separate from the pure potential techniques that went into the previous theorem. This is more real PDE techniques. And this is local in nature as well. On the previous page, we were on a compact Calabi manifold. So here we're locally on a small patch in Rn, or R2, R to the power 2n, possibly. And, at least we are locally in Cn. So we're on some open ball V. And then we assume that we have a solution to this complex Monge-Ampère equation here. And I also assume that if I perturb it a little bit, I add a small u, then, sorry, it should be to the power of d here. Then I don't change the right-hand side so much. I change it with a small perturbation f, which is small in ck minus 2 norms. So f is small and all of its derivatives are small. And I also assume that the supremum of u is small. If I know this, then I know that all derivatives of u are small as well. So my v here is the solution, is the Calabi-Yau potential, and my u is whatever I add to this to get this real Monge-Ampère potential.
And the sub u less than epsilon is what comes from the previous slide.
Exactly. Yes. That's it. And this is needed. It's also you would. So this is called a stability estimate for this PDE, because it says that if I vary the right hand side a little bit, then my solution doesn't vary too much. But to have a stability estimate, you need some kind of uniqueness in your PDE. And here we're looking at real Monge-Ampère equations locally, and then there is no uniqueness at all. There's like large classes of solutions to the same real Monge-Ampère equation locally. So you need something to kind of rule out, or to sort of handle this non-uniqueness. So this is then, in some sense, the best you can hope for. So it's a very strong theorem in the sense that as long as you know that you're close in a C0 mode, it means that when I vary the solution, then I have to vary. Then it also varies in a C0 setting. It doesn't just vary in a C2 or C3.
But isn't there some sort of uniqueness theorem, like it's old 70s? There's a boundary over the problem. The solution is unique.
If you have with the boundary value problem, exactly. So if you have if you fix u and you fix the u1 and u2, they convex, then there exists a unique solution u to the real Monge-Ampère, so determinant second derivative of u equals 1. Switch this to v, such that the gradient image used in nabla as before, nabla v equals u2. If I fix my domain and I also fix my gradient image, this is called the second boundary condition. Then I have uniqueness of solutions. But this also means that if I fix the domain, then essentially for any choice of target for the gradient, I get a different solution to my real Monge-Ampère equation. So that means if you, like in this theorem, if you look locally, I mean, there's no boundary conditions here. So you really need something to handle. So using this theorem, this essentially C infinity convergence, the potential follows. And once you have this, then the exists. So that means that the Calabi-Yau metrics are on this analyte, they are C infinity close to semi-flat Calabi-Yau metrics. And once you have that, there is you do this perturbation argument by sign, which is essentially an application of the implicit function theorem.
All these omega t are Calabi-Yau metrics.
Yes, indeed, yeah, right here.
They are Calabi.
So there is so that means that these sort of local special Lagrangian torus vibration we have for the real Monge-Ampère potential, they can be deformed just a little bit, and then they become special Lagrangian torus vibration for the Calabi-Yau.
In
some generalization of this theorem in which the omega t are not Calabi-Yau approach and omega that is Calabi-Yau. In the sense that we explained yesterday.
Maybe. So here I'm also assuming that okay.
How do you define special Lagrangian?
With the big omega.
Big omega. Okay. But how do you define Lagrangian?
With respect to omega t.
Okay. So omega t is just a
Small,
complex form.
big omega with respect to small omega.
Yeah. And so this is, and then it's not a Calabi form anymore, but
It is the was
It's not equal to the volume.
okay, right. I don't know. And I don't see any obstacles, but yeah.
But I think special Lagrangian it's really makes sense really when the unit it's
I know, but we want to approximate the Calabi-Yau metric and we may have Lagrangians with respect to the metrics that approximate the Calabi-Yau metric, and they are better and better with respect to the big omega. So they could converge to specific.
So if you don't, I'm going to move on to.
Yeah,
I'm going to move on then. I'm going to go back to this toric setting and talk about solvability of this real Monge-Ampère equation. So first of all, this real Monge-Ampère equation, it does admit a solution if y is pd plus 1, so we have the standard unit simplex. And this weight function is the trivial weight function. So h0 is 1 if h0 m is 1 if m is a vertex delta and plus infinity delta. So this is, for example, the dwarf family. Well, this is essentially the dwarf family. Then there exists a solution. This was proved by Yang Li in his first paper about the Fermat family, 2019. This was, and then it was sort of extended in various subtle ways. First of all, first by Phil Schneider, and what he did here, he actually used a statement about the non-Archimedean Monge-Ampère equation. Using with this solution to the real Monge-Ampère equation, he was able to show that because it exists, it has to be the same as the solution to the non-Archimedean Monge-Ampère equation. So there's an argument for that. And then he used the uniqueness of the non-Archimedean Monge-Ampère equation to show that that you had uniqueness in for this real Monge-Ampère equation. So that's when he actually used that framework. So he could prove uniqueness of solution, which actually gives a different statement in this SYZ business, because it removes one point where Yang Li had to pass the subsequence. Secondly, this was sort of proved again, but with some extensions by Mattias and Enrica and Nick together with me. And I think the main point of this is that we introduce a variational approach to this real Monge-Ampère equation. So the solution psi minimizes a certain function, which is given by integrating over the boundary of the moment polytope and the boundary of this dual polytope. So I integrate my potential here with respect to this integral measure, and here I integrate a transform of psi, the psi transform, which is very similar to the Chandra transform. psi c of M is the supremum of where we let M be this boundary of M paired minus psi. Okay. So, and this is this function is quite attractive in a few ways. First of all, it's symmetric, produce this symmetry. So there's here it's good to compare with this Batira mirror symmetry of toric data, where you somehow start with a Calabi-Yau hypersurface and a toric manifold, and then mirror symmetry corresponds to switching these polytope and dual polytope. If you start with a reflexive polytope, you can do it.
Can you comment on this? Is it smooth? I mean, that you just do the maximum with the boundary.
Which one is smooth?
Psi C.
Psi C. So this, if it will be smooth, it will be continuous.
That's not smooth because
No. It's hard to even talk about smoothness on the boundary.
Yeah.
You can talk whenever you have an affine patch. You can talk about smoothness, and it will actually be smooth in some cases. I'll talk about that as well. So we have this symmetry in where you can sort of switch these, and it's really the same functional. And that means also we have so whenever we get or let's maybe I'll get back to that. Another nice feature of this is that the functional is independent of location of this discriminant locus, which we specify. Location of discriminant locus. This is somehow a way to solve this Monge-Ampère equation without first specifying where the singular locus should be. So hopefully then the location of the singular locus could actually emerge from this solution. Then there's also a gradient map. So there is this, I should say, a multi-valued. Sorry about my handwriting. So there's a multi-valued gradient map, nabla, C of C. So at C. This is the set of all M such that psi of M n plus psi C of M equals this is like the generalization of the normal multi-value gradient map in convex geometry. So there's a gradient map then, and this goes from the boundary of this to the boundary of the Monge-Ampère. And lastly, one nice feature as well is that this is the Kantorovich dual of an optimal transport problem. Sort of makes it possible to study this thing using optimal transport. And this, so I will get back to some of these things later on. So this Monge-Ampère equation is also known to admit solutions in some more cases. So if we have the trivial height function and the polytope, the moment polytope and its dual satisfies that any two vertices of these two, the moment polytope and the dual, has non-zero pairing, then it's known that this equation makes a solution. And it's also, so this is due to Yang Li, and this also uses the same variational approach. And this Monge-Ampère equation, it admits a solution if and only if this pair, YH, is stable in a certain fashion. And this is stable in terms of optimal transport, so I'll talk a little bit about it as well. In particular then, if Y has many discrete symmetries, so in particular if the moment polytope is a Weyl polytope, so if it's the convex hull of an orbit of a point under a weight loop, then it's stable in terms of optimal transport and then it emits a solution. And in fact, in this case, we can even say more. When we have many discrete symmetries, then the discriminant locus, so the set where sort of our affine structure is not defined, then this will be the sort of is as expected, or you can choose it as expected, and psi is smooth on its complement. So when I say that you choose the discriminant locus as expected, then we are in this very symmetric situation, so then you just pick it by taking a barycentric subdivision of the codimension 1 space. So that's when you get this Y-shaped singularity, for example, in 3 dimensions, and that's also when you get the midpoints of the edges in the previous image I did. So in particular, so for example, in this case, when we have the then, or I guess I really need, okay. So here is my delta, here is my Q1. Then the discriminant locus would be the midpoint of the edges, and this potential will be smooth outside of this. That means it also defines like a really defines a Riemannian metric Monge-Ampère type. So you really get the Riemannian metric on the base, which then you can start talking about this global house convergence.
When you say the Weyl group is the root for the simple Lee algebras, is the root system, the convex hull, is it a reflexive polytope?
Yes, it should also be a reflexive polytope.
But is it always or no, it's not?
No, it's not always.
But for AM, is it reflexive?
I don't know. So so it is, for example, these in 2 dimensions. This one is a Weyl polytope.
So what is Weyl polytope?
Sorry.
What is Weyl polytope?
Maybe I can get back to your question later on. I'll just quickly I'll do some examples now. Like this. This is also a Weyl polytope. So you have these. They're very like the discrete symmetry group is vertex transitive and place transitive.
You take the convex hull for root system.
No, this is only the.
I fix a point, and then because this root system has these reflections, and then I fix a point, and then I take the orbit under all of those reflections. Okay. So and then about I didn't really mention Gromov-Hausdorff limits when I talked about Yang-Lee's results here. So you don't actually get Gromov-Hausdorff, or like once you have this C infinity convergence of the potential, then it's natural to ask for Gromov-Hausdorff convergence. So I mean, then you can ask, for example, if I take my xt's, will this converge together with the so I have my xt and omega Calabi-Yau. these as metric spaces. Will these converge to say let's say we do the boundary of the dual polytope, and I subtract this discriminant locus, I'll write sigma for discriminant locus, and then I equip this with this Monge-Ampère metric we had. I take I mean, this is an open set, but then it's natural to take the closure of this. This is a natural question. Like, will this converge to this? And then you could also ask as well, like, another question you can ask is this closure homeomorphic to ST? It's also a question here. And in terms of Young-Lee's machinery, it doesn't quite give Roman-Hausdorff convergence. You need essentially control everywhere next to get Roman-Hausdorff convergence. It's like if you don't have control everywhere, you cannot rule out like the existence of very short paths. But you get some kind of local Roman-Hausdorff convergence. There's a statement that involves local symmetries, which you can write down. So how am I doing with time now? 3 minutes. Okay. So I think I will talk. I'll just mention quickly in words, but I don't want to get into it. This fact that we had this. If you don't live here in this optimal transport state, it's actually quite easy to produce counterexamples where it's not stable and where there is no solution to the real Monge-Ampère equation. But then, as I said yesterday, you should interpret that as sort of the ambient space being the wrong ambient space. So what you should do then is probably somehow change the ambient space if you wanna apply these exact methods. And of course, the existence of a solution to the real Monge-Ampère equation in the non-Archimedean setting, it's a strictly weaker statement than looking for something which is toric. So in toric, there's no reason to believe that these semi-flat metrics should come from an ambient space. So I'm gonna talk a little bit more about these solutions. So one question which is natural to ask is like, so here we get an actual Riemannian metric on the base of Monge-Ampère type. So will this, as we talked about before, can this be just Euclidean on the open faces? And if we expect to have non-trivial holonomy around these singular points, then it can't be Euclidean actually. It is this sort of formal argument that what we have here is really like SD equipped with a flat torsion free connection and a Riemannian metric of Hessian type. And then if this Riemannian metric of Hessian type is actually a quadratic form, so given by a quadratic form, then that would mean that the flat torsion free connection is actually the Levi-Civita connection of the metric, which means that we would get trivial holonomy. There's sort of no way to extend this Euclidean metric into like a Monge-Ampère metric on something which is defined everywhere by the four dimension tools. So these solutions you get here, they are really non-explicit in the same way that the Calabi-Yau metrics are very non-explicit.
Can we do something numerical? Just get a feeling about what they look like?
Yeah. Then you have. So here is numerical computations. So here we are looking at the unit simplex, and I've taken, so this is like down here, I have the image of a star under one of these coordinate maps. So I start with this thing, and then I map the same star of this. Down to, and what does it look like when I map something down there? It sort of looks like this. And I guess something like that. So, and one thing that you should note here is you have this crease that goes down here. But the crease, like if you look down here, it looks pretty smooth. And if you...
So, in a central region is close to being parabola.
Just looks like that, but yeah. But well, it can't be a parabola. It's a wrong one.
But the holonomy is along the edges, right?
It would be, so, yeah, let me show you where the holonomy is. I mean, then it would be like, if you traverse that, it would be like going, yeah.
But in this dimension, I think we know what's the asymptotic x log x, right?
Oh, you mean near the...
Near the focus.
Yes, you do. But it's okay. But, okay. So you know that the asymptotic is near a singular point. Yeah. So what I wanted to show with this image is how the location of this discriminant locus kind of appear in the solution to PDE. So here's another image where I put my eye right here and I look at it from this direction. And it looks like this. And then it's more obvious that it's smooth down here, but there is a certain point somewhere here where this kink starts to develop. So it's from here and upwards, you have this singularity. And this kind of tells you that the patch you can use is that you should sort of exclude this part from the patch. And I mean, in this case, everything is symmetric, so it's actually happening exactly on the midpoint of this edge.
So once you pass this point, this is again smooth, but it's just in a wrong affine.
Yes, once you pass the point, you just need to change the chart.
Kind of kink is all the same level.
Yes, exactly. So then you have switch chart. Look at the chart here. And then you have something which is smooth here, but becomes kink start on the other side. So when you switch charts, you also need to do change the trivialization.
So what's the kind of PDE problem that you solve for this picture?
There's actually no apparent PDE problem. It's really just minimizing this function I talked about. That's also where the stability condition comes in, because there's always a minimizer of this functional, but then there is for this to actually have the right PDE properties, it needs to satisfy a certain stability condition.
But you can't tell the locus where the discriminant locus.
I can't compute it
from the. I mean, because it's insensitive to the, as you said, right? This functional that you minimize is sensitive to symmetry. But precise level. This is kind of strange.
Do you know what that's real or little?
No, I don't think I know. So it sort of appears as so one way to write down the way it appears is if you use this gradient map, then you can pull back the open faces to your polytope, and then you can pull back the full dimension one face to your polytope, and then the discriminant locus will be the intersection of these two polytope things, like maybe I'll just new page. So we have this gradient map, which is a priori is a multi-valued map, but some things are known about it. There are certain monotonicity properties of it. Then you pull back to get where the discriminant locus is. You pull back this codimension 1 skeleton here, and when you pull it back, you get something which looks like this. And the singular points will be the intersections. So here, like, there's some hope to say things, to prove things here, because you have this monotonicity property. For example, this one, like when I move along this one, I cannot move downwards here. I have to move upwards. It seems like they should sort of cross in a decent way, but it's you need a little bit more to be able to say it. So now, in principle, you could have something that travels up this thing, could go like this, and then suddenly jump sideways and continue upwards. So we actually we cannot even bound the Hausdorff dimension of this intersection. Ideally, if we have some kind of they intersect properly, then you get a bound on the Hausdorff dimension. But at this point, we're not there. It seems like it really becomes a question, like a regularity question for connected to optimal transport problems. So I talked about this the gradient map here. You can also think about that as a transport map. It's you have these two measures on the boundary of these polytopes, these two integral measures, and then this is actually going to be the cheapest way to transport all the mass on the boundary of these ones to the boundary of this. That's why you have this monotonicity property with this now. If you have a transport map which kind of goes like this, that means it's not effective, it's not cheap. I might just mention really quickly one statement that sort of regularity theory would give, and that is so I talked about the Gromov-Hausdorff limit here. One question is the Gromov-Hausdorff limit, then you need a lot of control, but like disregarding that for the moment, you could ask what is this? What is the closure of this real motion time metric? And in the so there is a theorem. So it's Rolf, myself, Mattias, and Enrica, that says that the solution is it's C1 alpha on the so it's symmetry group. Or it's weight photo. So what does this say? Well, it gives so we know that it's smooth on the regular part at the base, but this also gives like a uniform bound as you approach the singularities. So with that, you could hope to control like what the closure here really is, but you can't actually need something stronger than this. So this is enough in the two-dimensional case. So if the base is two-dimensional, then the closure of this is actually the sphere. But to prove this in general, you would need some kind of C2 alpha bound, at least sort of tangentially, as you approach the singularities and look tangentially to the singularities. I think that would be possible to get, and if you have that, then